All right, so it's a streaming time. All right, hello everybody. So okay, so you can see that today it's a little bit different. So I'm here and I'm showing like, and I'm showing like two different applications. So on the left side is the RoamResearch and on the right side is the Chrome. So basically, I'm going to take notes in RoamResearch while I'm like learning something, and on the right hand side, we will like search something else. Yeah. So on the left we will take notes, and on the right we will doing some search. And if I'm going to like show like a PDF or other things, and we will do that. I mean, I think it would be like really interesting to like doing in this way, because like I want to learn something. So when I'm like reading something, I can talk out loud, and it will also be interesting to like go through this journey together. So like if I want to learn something, and then we can like figure out it together. All right, so what are we going to learn about today? I mean, I'm thinking about like, so what I'm trying to learn is, so it's like, so the stuff that I'm trying to learn is like machine learning for material design. That's just the machine learning for material design. Okay, so this is what I'm going to learn, something like that. But like, how can we really like do it? What kind of things that we're trying to learn? I mean, for example, right? I mean, machine learning for material design. I think there is a very specific point in here. So we need to define questions. So I think we really need to define questions, what kind of things we want to build on, right? So, I mean, for my side, I would like to build like derive the interatomic potential from machine learning, and first train set of data. So basically it's like, what is the interatomic potential? Basically, interatomic potential means I want to train, get a force field that can generate potential energy signals of the system. So let's search something. Potential energies. Surface. All right. So we can copy this image to here. All right. So this will be. Yeah, maybe this one is better. So this will be our like potential energy surface. And what we are trying to do is that we know that like giving so I will giving like a set of atomic coordinates and trying to predict two things: so energy system, force at each atom. Yeah, so basically like this. So we want to derive the interatomic potential from machine learning. We want to derive the machine learning based interatomic potential from first principle data. This means DFT simulation. All right, so we're going to get this, and what we really want is we want to get a series of atomic coordinates, and we want to get the energy, and we want to get the force on each atom. Like if we want to get if we can get this correctly, which means we can do molecular dynamics, or we can do the Monte Carlo simulations, because I mean both Monte Carlo simulations and molecular dynamics depends on the potential energy surface. If we can find a machine learning model that can be used to approximate the potential energy surface, and I think that will be a very cool idea. All right, so that's basically the problem that what we are trying to solve. Define the questions. Get machine learn interatomic potential. Yes, like this. And next we would want to like machine learning approach. So basically in here, the machine learning approach right now, what I think would be important, like two things. One thing is like Gaussian approximation potential, what we call gap, and this is the kernel method, which means that it will search for a set of structures like a basis, and it will generate a linear combination between different kernels, and we can like define kernel in like this way, and Ri like reference. Okay, why is it not good? Maybe it's because maybe it's this one, RI. Yeah, it's like this. So the kernel basically means that so in here it's a kernel function, and this we can call it a kernel function. Determines the distance between two structures. You can also treat it like the similarity of two structures. So this is the Gaussian approximations, and the other one is we all know is the neural network. This. So basically, like define the question. So right now we are doing the prediction. So right now we're doing the prediction, and we can also doing another thing is called the generation. Generation will be the generative model. So this will be very different from the first class. So first class is the prediction, which means that, okay, I have the data, but the second one is that, so the first one we're trying to learn like the potential energy surface, but the second one is we're trying to learn the probability distribution of the ground state, because we want to predict some chemicals which are in the ground state which are stable. And it's the neural network. Okay, so here's the machine learning models. So once we have the machine learning model, it's not enough. We also need to have the data. Training data. The training data usually comes from like two different sources. One is the DFT simulations. It can be relaxation, or it can be like single point calculations. And it can also come from the initial molecular dynamics. So for example, the DFT simulations, you can from VASP or from quantum espresso. And for AMD simulations, you already come from VASP or like CP2K, or maybe someone who CPMD. It can also do that. So these are kind of softwares that you can use in order to do those kind of simulations. And so here are our training data. But it's very important to like provide an active learning strategy. Basically means that how to generate the training data gradually, like step by step. And this needs some different algorithm in order to do that. And I think so for right now, but I think in the future we're going to like read different papers and trying to really understand what they're talking about and what are the most important part of that, and how does this so how do they actually implement it. Then for example, maybe they're implementing a code, whether this code is like open source or not. We're going to dig really deep into that. And I think by like making those kind of learning streamings is also really interesting, because I mean, sometimes we learn something, but we really don't know like how do we actually learn, what is the journey about. But I think with this kind of documentation, then I know, okay, I want to learn this field. What is the initial phase that I have been through? Because I mean, sometimes I think it's really, really hard. So if you are someone that is already familiar with something, it's really hard for you to get a feeling of what it's like to have zero knowledge. So from the beginning. But if I kind of document this whole journey and in my stream, then it will be like really easy or like interesting to say, oh, so I can know that in the beginning, I just like everybody else, I don't know anything, right? I have to build something from the ground up. And I think that would be very helpful. Yeah. All right. So yeah, so the active learning strategy. And once we have this, once we have the training data, once we have the machine learning models, yeah, so then basically that we are trying to learn different kinds of methods. Okay, so we want to specify the learning goal. We want to know everything about this topic, which means that we need to look at the theory, we need to look at the implementation, and we also need to look at the data and also code. These are really important. So theory, we need to understand, okay, what is the theory behind that? And the implementation basically means, so implementation, I think it's similar to code, so I will delete that. Theory, data, and code. And we want to understand the difference between different approaches and be able to compare them with their. This is also what we want to do. We want to compare like different methods according to like maybe their, so there are like maybe some criteria, for example, speed and the requirement for the size of training data, maybe inference time, like its accuracy, whether have like mature code or not. And along this way, we will also like learning something very exciting. So for example, if I have a machine learning model, right, how do I like implement a machine learning model from scratch? Basically means that what kind of package we should use, and how do we build like the neural network, like the training and the whole thing, like from the ground up level, what kind of different things we need to consider. I mean, right now I have no idea about any of them. I'm just a beginner, right? But I think gradually, like when I'm learning more and more things, it will become like more and more clear. Implement a machine learning model from scratch, yeah. And also about the speed. The speed is also important. Speed, parallelization, and also like profiling, like finding out where is this source part. Yeah. So basically, we're trying to build this kind of like research platform, because I mean, basically, like, well, computational chemistry, right? What we're doing is computational chemistry. Basically means that we want to solve the Schrodinger equation, and we want to solve it like accurately and like fast. And how do we do that? You can can use the density function theory, but its time complexity is O(n) to the third, which means that if I double the number of electrons, the time will be like eight times longer. All right, so I guess, yeah. I guess we should start with some, so I think we should start with like a list of machine learning models. Okay, here's the list of machine learning models. And I will do like this. So basically for the machine learning model, here, for any machine learning model, we will have like two things. One thing is the feature vector. The other one is machine learning architecture. So the feature vector basically means that, okay, I have a Cartesian coordinates. This is the basis of like everything. So basically, in the beginning, like every chemical system can be represented by a set of Cartesian coordinates, like, yeah, like this, a set of Cartesian coordinates. And we need to find different features to represent it. Yeah, so we need features, we need like machine learning architectures, and I'm going to like organize them in this way. So for that, we should read some like literature review. All right, I mean, machine learning in okay, I think what we can do about this is that, okay, so basically what we would like to, so basically when we're trying to learn something, right, we're trying to so basically what we are trying to learn something, it's like a island. Let's see what do we have. high silent picture. Okay, maybe this one would be cool. Yeah, so like learning something is like what we're trying to do in the beginning is that we really don't know where to start, because you can start from anywhere, but it is important to, it's like start somewhere and just go along with your instinct and try to map the whole island, branch from what you have learned. And if you have done this long enough, you will learn the whole island. So I think it is really important, like when you're trying to learn something, don't try to like, oh, where should I start? You can start from anywhere, but as long as you follow like your thoughts, like, okay, I'm trying to understand this one, maybe here's a little bit part that I don't understand, and then you can dig on that, and then you figure out, okay, in order to understand this one, maybe I need to understand that one. So it's like building a tree. It's like building a graph, like your knowledge graph. And I think this is very important, and that's why we can start from like anywhere, but we would like gradually like learn more and more stuff together. Okay, so yeah, list of machine learning models. Let's go. Machine learning. Okay, so if I open this, will we be able to see it? I don't think so. So maybe I should add another one, like macOS screen capture. This is a preview. No, application capture. A fast preview. Okay. Yeah, so it's really large. What is this? Okay, it's RoamResearch. Not application capture, window capture. remove preview. Okay. Yeah, I mean, I think we can just read in here. I think it'll be better. Yeah, okay, good. Okay, so I'm going to shrink myself a little bit. Put it here, yeah, so we can. What is this part? RoamResearch here, and Chrome is here. Chrome maybe a little bit. Okay, just move it a little bit to this side. Yeah. All right. I guess it works. Yeah. Use machine learning in materials design. Okay. Giving a number of examples. How's this? From large databases, for example, those generated by high throughput DFT simulations. Okay. Yeah. Also, I think it is really important to understand different words, right? So in here, I'm going to create like a vocabulary set. So basically, every important vocabularies I will be summarized in here. Vocabulary side, I think should be a separate. So vocabulary set, for example, like this. So high throughput DFT calculation. There's one how they can be made from experimental growing smaller databases. Active learning. Additionally, we'll discuss such advanced machine learning methods, multi-objective and multi-fidelity. This is a really big word, multi-objective and multi-fidelity optimization. So multi-objective is quite easy. So multi-objective basically means that I'm not going to optimize one thing. I'm going to optimize a lot of things. That's multi-objective. Multi-objective operable optimization is an area of multi-criteria decision making. Okay, multi is a type of vector optimization has been applied in many fields of science. Vector optimization. It's a vector valued objective functions optimized with respect. Yeah. So, which means that the optimization is not technically one value. This means the objective or the label is not one value, but instead a vector. Multi-fidelity optimization stands out as a cost-effective strategy, balance high fidelity accuracy with computational efficiency. Okay, what is this? What is high fidelity data? Maximize accuracy or minimize the costs. Okay, low fidelity data. Ah, okay. Multi-fidelity optimization basically means that uses different level of, for example, DFT. For example, PPE, scan, PPE scan, or like other HSE, or like higher level of simulation, like different level of DFT, then combine them together in order to get higher accuracy. So, I mean, it's like fidelity of data, low fidelity data, high fidelity data, hi-fi. So low fidelity data means was produced by a person or stochastic process that deviates from the real world system of interest. The data that deviates. Deviates the word of interest, and high fidelity data includes closely matches the operational context of, okay, yeah, I mean the multi-fidelity methods each data source while overcoming the limitations, although small to medium differences between low and high fidelity data sometimes able to overcome by multi-fidelity models, large differences can be problematic, leading to decreased predictive performance. Yeah. I think that is also important. The data that closely matches the functional. That permit proposing new materials with simultaneous optimization more than one target property. Using field cost. Yeah, so with low heterogeneous and high curing temperature. This basically means this one. Example design of materials and this one. Using field custody experiments. Okay, so I think I also need to build like a literature bank. The first thing is this one. Conclude brief discussion, future machine learning opportunities in the context of high throughput experiment, on the fly adjustment of synthesis. Using machine learning methods to aid is a rapid growing area. Yeah. Fueled by the presence of a massive materials genome initiative. Basically lead to the development of materials products. Is the maintenance of our country's manufacturing. Okay. We want to discover game-changing materials. Always one more properties lie far beyond. Okay. That is much more data and computation driven than in the past. Computation creating large databases. Machine learning methods are the main tools being used to facilitate the exploration of this data. There's hope and reason to believe that these methods, when applied, properly crafted material bases and properly used, will augment, in many cases, supplant the time consuming. Yeah, this is good. Convey some lesson learned. For example, to date, much of the use of machine learning methods has been strongly coupled to nearly simultaneous generations of large databases. Use of less common machine learning tools made it possible to grow small, experimentally generated databases into larger ones, along the way to predict new materials. In the context of non-high throughput activity. Identifying a few possibilities at a time that will make the most difference with respect to what we presently know. Computing these possibilities as accurately as possible and verify them experimentally. Okay, so basically what they means is that we don't need to calculate like every single thing. We just need to choose a selected like subspace, and we're trying to get that as accurately as possible. Multi-objective optimization, yeah. Multi-fidelity optimization, yeah. permit the combination of calculations with different level of accuracy, experiments with different measurement precisions. Yeah. Discuss some newer methods and more importantly reference their success. Okay, good. Philosophical descriptions of machine learning. What is it? It's not physics, chemistry, or material science. How does this domain knowledge enter? It's largely several applications with different machine learning, not cases where the predictions have been validated. Illustrates the broad spectrum of applications possible. Yeah, I think it is important. I mean, but let's just take a look at the things. Machine learning, large databases. Yeah. Small database examples. Okay. Front, multi-objective optimization, multi-fidelity. Okay, basically like this. Basically like this paper is really focused on the multi-objective optimization and multi-fidelity optimization. So this paper really focused on like these 2 points. Okay, let's start with this machine learning. Gradient tree boosting method. Here's the gradient tree boosting method. Gradient boosting is a machine learning technique based on boosting. What is boosting? On boosting in a functional space where the target is pseudo residues rather than the typical residues used in traditional boosting. Gradient tree boosting. Decision trees. Okay, gradient boosting. In machine learning, there are many generic tasks. It's not just the source. What defines the discipline using any of these methods is not just the source of the data and the information sought from it, but also the parameterization of the data. The parameterization defines the variables we use in the machine learning, called the features, sometimes called descriptors. The features are ultimately the main portals for the science. Features, descriptors, main portals for the science. I think today I'm going to like call it right now because it's already like 12:33 and I'm so tired right now. So I'll have a very good sleep. Maybe tomorrow I can like doing it longer. Yeah. All right. So see you guys tomorrow. Tomorrow I think I will do a work stream first. Then we will start like this learning streaming. I mean, I think the work stream and learning stream will be different because the learning stream is really about how we can like figure out ideas together and trying to like map this whole area by ourselves, like really understand each concept. So yeah, so I think it'll be very fun. I mean, Andrew Kapasi said, if you want to like learn something, like try to put 10,000 hours into that. So this is just the first hour that I'm putting into. So let's see what will happen in the 10,000 hours. All right, see you guys tomorrow. Bye bye.